This splice has a loss of minus 0.05 decibels. At least, that is what the OTDR says. Has an ordinary connection just amplified the light? Of course not. This is a gainer, an apparent increase that can send a technician back to rework a perfectly good splice. In the next few minutes, you will see what an OTDR actually measures, where the trace comes from, why a longer pulse helps and hurts at the same time, and how a dirty connector can blind the instrument. We begin with a single pulse of light. An OTDR, or optical time domain reflectometer, launches a short laser pulse into the fiber. It does not watch the light arriving at the far end. It listens to what comes back. The first mechanism is Rayleigh scattering. Microscopic variations in the glass scatter light in every direction. A tiny fraction returns to the detector along the entire length of the fiber. This continuous weak signal draws the sloping baseline of the trace. The second mechanism is Fresnel reflection. It appears wherever the refractive index changes abruptly, at a connector, an air gap, a crack, or the end of the fiber. Instead of a smooth line, we get a strong peak. The OTDR measures return time. It calculates distance from the equation, L equals C times T, divided by 2n. The factor of 2 is there because the light travels out and back. The value n describes how fast light moves through the glass. An incorrect index of refraction does not change the trace itself, but it shifts every event along the distance axis. Every shape on an OTDR trace carries information. The slope of the line is fiber attenuation, expressed in decibels per kilometer. A downward step is a power loss, for example at a splice or a bend. An upward peak is a reflective event, usually a connector or the end of the fiber. The jagged cloud at the end is noise. The returning signal has become too weak. One pulse is not enough. Backscatter is extremely weak, so the OTDR repeats the measurement many times and averages the samples. Longer averaging smooths the trace, but it cannot fix a poorly selected pulse, a dirty port, or an event hidden inside a dead zone. A short pulse gives high resolution. Two connectors separated by only a few tens of meters remain distinct, and the dead zone after a strong reflection is short. The price is lower energy, more noise, and less range. A long pulse carries more energy. The trace becomes smoother, and the OTDR can see farther. But the reflected peak becomes wider, the detector takes longer to recover, and nearby events can merge into one. That is why, on short and densely populated links and in passive optical networks, we begin with pulses of about 10 to 30 nanoseconds. Long backbone links may require pulses of 300 nanoseconds or more. When you need both resolution and range, take two measurements. Judge each event from the trace that shows it best. How do you measure splice loss when the trace itself is noisy? The simplest two-point method subtracts the levels of two individual samples. If one marker lands on a local maximum and the other on a minimum, the result can fluctuate more than the loss being measured. The least squares approximation method works differently. On each side of the event, it selects a clean section of backscatter, fits a straight line to dozens of samples, and extrapolates both lines to the center of the event. The vertical difference between the lines is the loss. Noise is averaged out, so the result is much more repeatable. This is the basis of the 5-marker measurement. There is one condition. The least squares windows must not include another splice, a reflective peak, or the end of the fiber. Mathematics cannot rescue badly positioned markers. The first connector in a link is usually hidden beneath the large launch reflection. Without additional fiber, it cannot be evaluated reliably. A launch fiber, typically 150 to 500 meters long, moves that connector beyond the dead zone. At the far end, the problem is reversed. To calculate the loss of the final connector, the OTDR also needs a backscatter level beyond it. A receive fiber provides that reference. The ref and end markers define the actual link, and event distances are measured from ref, not from the OTDR port. Let us return to the splice from the opening. An OTDR does not directly measure the power transmitted through an event. It compares the backscatter level before and after it. Two fibers can have different backscatter coefficients even when both comply with G652D. When the OTDR moves from a darker fiber to a brighter one, the trace rises after the splice. The instrument reports negative loss. Reverse the direction and the same splice appears excessively lossy. In one direction, the result contains the real loss plus the backscatter mismatch. In the other, it contains the real loss minus the same mismatch. The arithmetic mean cancels that error. Here is an example from our training materials: minus 0.231 decibels from A to B and plus 0.257 decibels from B to A. The average is 0.013 decibels. That is an excellent splice, not a candidate for rework. This is why the real event loss is determined by bidirectional measurement. A one-way result is useful for locating a problem, but it can be misleading from a metrology standpoint. The core of a single-mode fiber is about 9 micrometers across. A dust particle only 5 micrometers wide can block a significant part of the optical field. Worse still, contamination can create an air gap. At a glass-to-air boundary, up to 4% of the power returns, which is about minus 14 decibels of reflectance. For comparison, a clean APC connector typically falls below minus 60 decibels, while UPC is around minus 50 to minus 55. A dirty OTDR port creates an enormous launch peak. The detector saturates, the dead zone grows, and part of the dynamic range disappears. The OTDR becomes blind exactly where you need to see the first events. If the same suspicious peak appears at the same distance on every fiber, inspect your own launch lead first. The procedure is simple: inspect, clean, inspect again before every connection. A dirty plug contaminates a clean port, and a dirty port contaminates the next plug. In a passive optical network splitter, power is divided among multiple branches. Every doubling of the number of outputs costs about 3 decibels plus excess loss. A 1-to-8 splitter typically introduces about 10.5 decibels. 1-to-64 is about 20.4. On the OTDR trace, that looks like a huge non-reflective step. It is not a fault, and it is not a terrible splice. In passive optical network mode, the event must be identified as a splitter and evaluated against its own threshold. A normal splice limit would fail it immediately. An OTDR is not an automatic verdict machine. It is a precision receiver for extremely weak light, and the trace is the combined result of physics, settings, and measurement procedure. Remember 5 things: the right pulse, clean connectors, correctly positioned least squares markers, a launch and receive fiber, and measurement from both directions. If you want to practice these skills yourself, visit the free Interlab Fiber Academy. It includes 6 chapters, an interactive OTDR simulator, end face inspection, attenuation, passive optical networks, and Tier 1 and Tier 2 certification. You can launch the OTDR simulator immediately, and free registration unlocks full access. Go to interlab.pl/academia/en. Set the parameters and watch the physics respond before your eyes.